Hi everybody, this video is going to be on section 10.5, Conic Sections. In this section, you actually aren't going to learn any new calculus ideas. This is really just going to be a review of all conic sections as learned in algebra and pre-calculus. Okay? We are going to focus more on where these formulas come from, so it is going to be quite a thorough overview. Okay? So, what is a conic section? If we intersect a plane with a cone, we get a curve called a conic section. So this is where the name conic section comes from. It's like a section of a cone. So there are three types of conic sections we will be studying. Those three are parabolas, ellipses, or ellipses, and hyperbolas. Okay, so let's go over the first type, which is parabolas. So let's do a definition here. A parabola is the set of points in a plane that are equidistant from a fixed point F called the focus and a fixed line L called the Directrix. Well, let me make that a little more clear here. Directrix. Okay. And I will draw a picture of this, so don't worry. The point halfway between the focus and directrix is called the vertex. And lies on the parabola. Okay, so I would like for us to have a picture of this. So I'm going to do this on the next page here. So here's our directrix. Let me use, here's our directrix. And here, we're going to call this point right here, this is our focus F. So what we want is we want the set of all points that are equidistant from this point and from the line L. So what do we mean by that? Let's try to draw a picture here. First, let's think about the point that's right in between. So let's say this point right here. Clearly this point has the same distance from the point F and the line L, right? So that point must lie on the parabola, and in fact that's called the vertex. Now let's try to draw another one that we think is on there. What about this point right here? You'll notice that if you look at this distance right here and this distance right here, they are the same. So therefore, it's on the parabola also. So if I were to make these guys darker, what we end up with is something that looks like this, right? And so what we're saying is that any point that we grab on here has to be the same distance to F as to L. So this is why we get that shape, and we do get the same shape on the other side. Okay, so this is called the parabola. Okay. Now, what I would like for us to do is to derive the equation. What is the equation of a parabola? So equation, derivation. I know we all know the equations of a parabola, but the point of this section is for us to derive all of the equations ourselves, just so we know where every equation comes from, okay? So here's what we're going to do. We're going to place, we need to draw a coordinate system, right? So we're going to place the vertex at the origin. So it's going to look like this. I'm going to draw a blue coordinate system here. What I'm going to do is I'm going to make this the y-axis. And then I'm going to make this the x-axis. This is x and this is y. Okay? So you could see that I put the origin is the vertex, right? Okay? And so where would the focus be? We're going to give that a point. We're going to pretend like this distance right here is P. In other words, now the focus is at the point 0P. Zero P. And what about the directrix? Well, because this distance has to match, this is also P, and so the directrix is going to have equation, and the directrix has equation. It's going to be y equals negative P, right? Because every horizontal line has the equation y equals something, and we know that it intersects at negative P. Okay, so this is what we have at this point. Now what we're going to do is we're going to take any point, and we're going to call this guy x, y. Okay, so there's our point. So let's let A be a point on the parabola with coordinates x, y. So what we need to do is we need to find a relationship, right? We need to figure out what equation that point must satisfy. So here's our point A, okay? So here's what we're going to do, right? We know, based on the fact that it's a parabola and we have a definition for it, we know that this distance right here and this distance straight to the floor or straight to the directrix has to match, right? So we know that those two guys are the same. So I'm going to put little squigglies here to show that those are the same. So that we should be able to figure out exactly what those distances are, right? Because what would this point be? Well, this has the same x coordinate, right? Because it's right underneath, except the y coordinate is negative p, right? Because it lies on the line. And then what would this point be? We know that F is the point 0, p. Okay? And so we know that the distance has to be the same, right? The distance has to be the same. So what would this distance be? We don't even need the distance formula to do this part, right? The distance from here to here is y plus p, because it's a height of y, and then we also went p more down. Okay? Now, what about this distance? The distance from A to F. That's where we actually need the distance formula. So what would the distance from A to F be? This is equal to the square root of, remember it's x2 minus x1 squared plus y2 minus y1 squared. So this is going to be x minus 0 squared plus y minus p squared. So this is the distance, right? So because the two distances have to match, this means that the green matches this, right? This means that y plus p is equal to the square root of, let's simplify that inside, isn't it x squared plus y minus p squared? So there we go. We now, the rest of what we're going to do is to simplify this equation, and it's really not that bad. We're going to start by squaring both sides. So if we square both sides of this, the left side becomes y plus p squared, and the right side, well, just the radical goes away, right? And we end up with y minus p squared. So let's go on to the next page. We're going to square the left out and square the right out and see what we get. We end up with y squared plus 2py plus p squared. And that's going to equal, on the other side we had x squared plus, and then we had y squared minus 2py plus y squared. But let's go ahead and cancel the stuff that appear on both sides, right? We know that the y squareds can cancel out. Oh, sorry, that last part should be a p squared, right? Here we go. So we can cancel a y squared from both sides, and we can also cancel a p squared from both sides. So what do we end up with? We actually end up with, so if we add the 2py to both sides, here's what we end up with. We actually end up with x squared is equal to 4py. Or another way to write this is y is equal to 1 over 4p times x squared. Why would we write it this way? The one on the right is if we want to write y as a function of x. So this is why I wrote it this way. And so this is our final equation for a parabola. Okay. Now there's something important to note is that this is only one type of a parabola, right? It's a parabola. We made an assumption that it opened up. And so I want to be more specific here, okay? So when you have this parabola, here is the info about the parabola. The vertex is 0, 0. Remember that. And the focus was 0p. And the directrix, let me back up here. The directrix is the equation y equals negative p. Okay. if p is positive, and that's the case that we did, right? In our picture, p was a positive number. This means that it opens up. If p is negative, then it opens down. Okay. This is not the end of the story, right? Everything that we did here, we can swap x and y. Okay, we could swap x and y. In other words, we could have instead made the directrix vertical, a vertical line instead of a horizontal line, and then our parabola would have opened to the right or the left. Okay, so let me go ahead and talk about that case really quick, okay? So if we switch x and y, we get instead y squared is equal to 4py, or y squared is equal to 4px, I apologize, or x is equal to 1 over 4p y squared. What happens here? Well, now the info changes, right? The vertex is still the same. The vertex is 0, 0. But remember, every x and y swap. So now the focus is P0. The directrix is x equals negative p. And if p is positive, then it opens right. If p is negative, then it opens left. Okay? I mean, I don't want to go too much into detail here because it's really not that different from what we just did, but just understand that now the directrix looks like that, the focus looks like this, and so if you were to draw this parabola, it would look something like that, right? So this is all we mean when we say opens right or opens left. See, now the directrix has an x equation instead of a y equation, and so on. Okay? Let's do a quick example before we move on. This will be example 1. I want us to find the focus and directrix of the parabola 2y squared plus 12x is equal to 0, and sketch the graph. By the way, before we do this problem, let's come back here. How do we know whether we're talking about a parabola that opens right and left or up and down? We know based on which variable is being squared. Again, that is the key. Every one of these conic sections that we write down, you're going to be able to tell which type it is. Okay, in this case, you could see that when the y is squared, we're talking about a parabola that opens right or left. And if the x is squared, we're talking about a parabola that opens up or down. Okay? All right, so let's go ahead and figure out this problem. We want to find the focus and the directrix and sketch the graph. So how do we do this? Well, we need to put it in one of the forms that we're familiar with, right? What I like to do is I like to isolate, we need to isolate the square here. So if we do that, we get 2y squared is equal to negative 12x. I just move the 12x over. And then I divide both sides by 2. This means that y squared is equal to negative 6x. We could see that this is the formula where y is squared. And if we look at our formula from before, we know that y squared is equal to 4px, right? Okay, what does this mean? This means that (4p) is equal to negative 6. or P is equal to negative 3 over 2, which, by the way, is a negative. What does that tell us? Either this opens left or it opens down, depending on which variable was squared. And because the y was squared, this means that it opens left. Okay, we know it opens left. So what is the focus then? Remember, the focus is always, in what we're doing now, the focus is P0, right? So it's going to be negative 3/2, 0. And what's the directrix? Remember, it's x equals negative p. In this case, it's going to be x equals 3/2. So let's go ahead and sketch a picture of this, okay? The focus is at right here. So this is our F. And then x equals positive 3/2. So here's our directrix. This is our directrix. And so what does our actual parabola look like? It looks like something like that. I don't want to confuse you guys. This is just my coordinate system. This is my XY axis. Okay, I'm going to put an X there and a Y, but my actual parabola is the thing that's opening to the left. Okay, really not that bad. You just have to make sure you remember these formulas. And again, this should all be familiar, right? This is all review of stuff hopefully you've already seen before. Okay, I would like to talk about the ellipse now. And by the way, you might be wondering, can't we translate these parabolas? What if the vertex isn't exactly 0, 0? What if we move it around? We're going to be talking about translations at the very end, okay? And how that affects all of these. It makes sense to talk about it at the very end so we can apply it to all of the conic sections at once, okay? All right, so let's talk about ellipses now. So let's give a definition of the ellipse, okay? So for this one, let's fix 2 points. We're going to call them F1 and F2, and we're going to call them foci. It's like focus, except there's 2 of them, so that's the plural for focus, okay? Foci. So what is an ellipse? Oh, sorry, there's one more thing I have to do, is I want us to fix a positive constant. Okay. So what is an ellipse? An ellipse is the set of all points P in a plane that satisfy the following property. The distance from P to F1 plus the distance from P to F2 is equal to K. So what we're saying is that if you take any point on the ellipse, if you calculate its distance to both foci and you add those distances together, you will always get the same constant. Okay? All right. So what does, let me actually draw a picture here. So if you have a foci, 2 foci, right, let's call these 2 points the foci. And we know what an ellipse looks like, so let's just kind of draw it, okay? What we're saying is that if you take any point on there, if you take that distance plus that distance, you get k. So if I call that A and I call this B, we know that A plus B is k. And also, if you take any other point, doesn't matter which one, so let's say this one. If I call this C and I call this D, then that means that C plus D also has to be k. It's true no matter what point you pick on the ellipse. Okay? All right, so again, we want to derive the equation, okay? So let's do the equation derivation here. So we're going to start by letting the foci, so let's let the foci lie on, so we're going to call F1 negative C0, and F2 is going to be C0. Those are going to be the two foci. And we're going to let K, the constant, be 2a. And this is allowed because any positive number can be cut in half, right? So really a is just half of the constant we had before. So let k equal 2a. And finally, we're going to say let P, which has coordinates x, y, be a point on the ellipse. So what is the equation then? Isn't it true that the distance from P to F1 plus the distance from P to F2 has to be k, or in this case 2a, right? Because we decided to call k equal to 2a. The reason for that, by the way, is that it's actually going to make our, just the formula at the end work out a little nicer if we call the constant 2a instead of k. Okay? All right, so what is the distance from P to F1? Well, we've got our points here, right? We're talking about the distance from here to here. So how do you do the distance from those two? Well, the distance from P to F1, just use the distance formula, right? So this is what it's going to be. It's going to be the square root of, so we have x2 minus x1, so it's going to be x plus c squared plus, and then we have a y squared, and that's the first distance, right? Plus the second distance is going to be the distance from P, so I'm going to do now the distance from this guy to this guy. Okay, so that's going to be only slightly different. It's just going to be an x minus c squared, and then plus y minus 0 squared again, so y squared. There we go. And so that whole thing has to equal 2a. Okay, all I did was I got this, and I actually wrote out what it meant algebraically. So now the rest of this is going to be all algebra, where we're going to take this underlined thing and we're going to clean it up so that it looks nice, okay? So what we're going to do first, whenever you're solving a radical equation, we learn in algebra that the best thing to do is to isolate one of the radicals and square both sides. So this means I'm going to isolate this left radical, x plus c squared plus y squared. And on the right, I know that I have 2a minus this other radical. And so I'm going to start to do the work now that leads me to isolate, or that leads me to get rid of the square root. So first, I'm going to square both sides of this. I end up with x plus c. You know what? I'm going to go ahead also and actually, oh yeah, that's fine. Let me write this. And then I'll do, on the next step, I'll actually expand that. So squaring that guy only gets rid of the radical. Now on the right, this is a little complicated. We're squaring this, which means we actually have to FOIL it out. So we end up with 4a squared and then minus 4a times the square root of x minus c squared plus y squared plus, and then we get rid of the radical for the last part. So this is what I get. Okay. What I'm going to do now is I'm going to square this out. So what does this become? So this guy is going to become x squared plus 2cx plus c squared plus y squared. On the right I have 4a squared minus 4a times this radical. And then I have x squared minus 2cx plus c squared, and then plus y squared. And let me go ahead and cancel the stuff that appears on both sides, right? I can subtract x squared from both sides. I can subtract c squared from both sides. And I can also get rid of the y squared from both sides. From here, I'm going to go ahead and move the other stuff over. So this is what I have now. I'm going to get the radical by itself. Okay, so the way I'm going to do that is I'm going to take the radical on the right and write it on the left. So this means that I end up with 4a times the square root of, and let me go ahead and expand what's under the radical. I have x squared minus 2cx plus c squared plus y squared under the radical, right? And that is going to equal what? So on the other side, here's what I have, right? I have, let me see, I have 4a squared minus 2cx. But look, I also have another 2cx. So these two 2cx's are actually going to combine when I move it all over, right? So what do I end up with? I end up with 4cx minus 4a squared. Okay. Now I can divide both sides by 4, can I not? Right? The 4 doesn't need to be on both sides. So if I divide the left by 4 and I divide the right by 4, what do we get on the next line? We actually end up with a square root of x squared minus 2cx plus c squared, and then plus y squared, and on the right I have cx minus a squared. So now what I'm going to do is I'm going to square both sides again, since I more or less got the radical by itself on that side, okay? So here's what we end up with. We end up with, so I have a squared times x squared minus 2a squared cx plus a squared c squared plus a squared y squared. All I did was I distributed a squared times everything under the radical. On the right side, I have c squared x squared minus 2a squared cx plus a to the 4th. So what happens? This guy cancels with this guy, right? Because it's the same thing on both sides. So here's how I'm going to write it, okay? This means, so I'm going to keep playing with this, okay? I have a squared x squared plus a squared c squared plus a squared y squared. This is going to equal c squared x squared plus a to the 4th. Now what I'm going to do, I'm going to take these x squared term, this x squared term, and I'm going to write it next to that guy. And I'm also going to take the y squared term and leave it on the left. And then I'm going to take this guy and move it to the right. And so this is what I get. If I take the x squared out, I'm left with a squared minus c squared plus, and then I have an a squared y squared. And this is equal to, if I move that a squared c squared to the other side, I end up with a to the fourth. So look, I have a to the fourth minus a squared c squared, but I'm going to factor out an a squared out of that. And so what I have on the right side is a squared times a squared minus c squared. Finally, if I divide both sides by a squared minus c squared, and also by a squared, what do I end up with? So I end up with three terms. The first term is going to be x squared over a squared plus, and then in my next term, the a squareds cancel, I get y squared over a squared minus c squared, and then on the right, I get 1. Okay? Okay. So from here, I want us to figure something out, okay? Because there is a nicer way that we can write this formula, okay? So let's look at the ellipse really quick. I want to do a little bit of thinking on the next page, actually, so that we can deduce a few things here. So here is our I know this is a rough picture here, okay? So all we know is that this point is C0, right? And we know that this point over here is negative C0. And so if we look at this distance right here, this is C, right? This is C. Now, look at this point up here. We know, remember, what we said was that this guy, any point on the ellipse has to satisfy that this guy plus this guy is equal to 2a, right? However, this is true symmetry. If this point is directly above this guy, it's symmetry. In other words, this has to be a and this has to be a as well. Okay? So what could we call this? If we call this point B, or sorry, not point, but if we call that distance B, in other words, this is the point 0B, we have the Pythagorean theorem, don't we? We know that B squared plus C squared is equal to A squared. Or another way to view this is B squared is equal to A squared minus C squared. This means also that a squared is larger than b squared, right? Because it's the hypotenuse of a triangle. Now these two facts are going to allow us to go back and write our ellipse equation even easier, because what if instead of a squared minus b squared, I replace it, a squared minus c squared, I replace it with b squared. So coming back here, this means I can rewrite my equation as follows. X squared over a squared plus y squared over b squared is equal to 1. Okay. And there we go. This is our ellipse equation that we are all familiar with. And so this leads us, there is one thing I should point out, okay? I want you to notice something, that if you were to plug in x is equal to 0, you actually end up with y equals plus or minus b, and this is what we were talking about. These are indeed the y-intercepts, right? This is the y-intercepts of the ellipse. And if you were to plug into this equation y equals 0, then that means that x is equal to plus or minus a. These are the x-intercepts. So going back to this picture, this means that if you were to actually look at your equation or your ellipse, we have the following. We have x squared over a squared plus y squared over b squared is equal to 1. The foci are at plus or minus c, 0. And we have a name for these points right here. This point and this point, these are called the vertices, okay? This is a vertex, and this is a vertex. And what are the coordinates here? Remember, those would just be the intercepts, right? Because we're actually putting our coordinate system right there. And so those 2 points would just be the X intercepts. In other words, this distance is just A, right? So this is just A. So what are the vertices then? The vertices of an ellipse are plus or minus a, 0. Okay. And where is C in the relationship here? The thing you have to remember is that C will never be in your equation. However, you can find it easily. Remember, A is larger than B. So A squared is larger than B squared. And the way you can remember how to find B is that C squared is equal to A squared minus B squared, okay? So this is always going to give you your ellipse, and your ellipse is always going to look like this. So it's something like that. I'm sorry, let me fix the end part of this. There's your ellipse, and this is a 0. This is negative a 0, this is 0b, this is 0 negative b, and your foci are somewhere inside this thing. So this would be c0, this would be negative c0. Okay, so this is your ellipse. Now what happens if you interchange x and y? So interchanging x and y. What do we get? Well, now we get y squared over a squared plus x squared over b squared is equal to 1. Okay, now how can we tell the difference between these two? Right, it's really hard to tell the difference because they're both with a plus sign, right? So how do you know which one is which? Well, the key is that A is always larger than B. A is always larger than B. That's how you know which ellipse we're talking about. So what would the foci be in this case? Remember, since x and y are swapped, 0 plus or minus c would be the foci, the vertices. The vertices would be 0 plus or minus a. And what would your ellipse? So it's still true that c squared is a squared minus b squared. And now your ellipse looks something like this. So this is 0a, this is 0 negative a, this is b 0, this is negative b 0, and then your foci are here and here somewhere, right? This is 0c, and this is 0 negative c. And these are your remember your vertices are always the tip. So these vertices right here, let me call it V1 and V2, right? They look like this. It's these points. Okay. So there you go. The way that you know which is, of course, A is larger than B, and therefore you know that it's a stretched out horizontally ellipse if the larger guy is underneath the y instead of the x, right? That's how you could tell these two apart. It's where the larger one is. So let me write this as a tip here. So tip, the foci are always in the direction of the variable with the larger denominator. The larger denominator, okay? So this is how you can tell which type we're talking about. All right, so let's go ahead and do an example here. So for number 2, I want us to sketch the graph of 225x squared plus 16y squared is equal to 400 and locate the foci. So the key to doing any example, I think, with conic sections is to try to put it into the standard form. In this case, what we're going to do is we're going to aim for getting a 1 on the right side. This is always the key for ellipses, okay? We're going to divide everything by 400. Okay, so if we do that, we end up with, how do you divide 225 by 400? Of course, that is not going to be, so this is not going to be a perfect fraction. So we end up with something like this. If we divide by 25, we actually get 9 over, 16? And then if we divide 400 by 16, we end up with 25. So it's something like this. How do we write that in the right form? Well, the trick here is to write it like this. So now we've written it in the right form, but we can all agree that this number, 25, is actually larger than 16 over 9. In other words, this guy is my a squared, and this guy is my b squared. So it's actually written in reverse order. Let me go ahead and write it in the correct standard form. Y squared over 25 plus x squared over 16/9 is equal to 1. So we're ready now to find our foci, and we can do that by finding c, right? We know that c squared is equal to a squared minus b squared, which is equal to 25 minus 16 over 9. So what do we end up here? So when I do that subtraction, we actually get 209 over 9. Which, if we put that in our calculator, just to get a decimal approximation, 209 over 9, the square root of that is about 4.8. This is going to help when we draw our picture, okay? Okay, so then what would our foci be? The foci are, 209 over 9 is not approximately, so I wrote this wrong. That's c squared, right? So c is equal to the square root of 209 over 3, which is approximately equal to 4.8. So this is what I was talking about. So c, remember, c is in the direction of the larger denominator, so it's going to be 0, comma, plus or minus root 209 over 3. So these are the foci. Okay. All right. So remember, it wanted the foci. We got those. And now we need to do a sketch. The sketch can help us here, right? If a squared is this, then this means that a is 5. And if this is b squared, then this means that b is 4 over 3, which is approximately 1.3, right? But we're ready to draw ourselves a picture here, okay? Remember, the 5 goes in the direction of the y squared, and the 16 over 9, or sorry, the 4 over 3 goes in the direction of the x squared. So we're going to put this guy here. So if I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. I may as well go 5 in every direction. So let's go back here. Remember, it said that we go 5 up, 5 down, 1, 2, 3, 4, 5. So this is my 5 up, and this is my 5 down. So those would be the vertices, and then we only go 1 1/3 to the right, 1 1/3 to the left. And so we have the following for our foci. I'm sorry, not our foci, but our actual ellipse here. So our ellipse looks something like this. This is 0, 5, and this is 0, -5, and this is 4/3, 0, and this is -4/3, 0, right? And what about our foci? We may as well throw those into the picture. Remember, we said it was at 4.8. So the foci are actually, I know I drew that way below, but it's actually supposed to be really close. That guy right there, this is the point 0 root 209 over 3, and then this point would be 0 and then negative root 209 over 3. So this is the focus, right? I can call this guy F2 and I can call this guy F1. It doesn't matter which one you call which, right? So this is the important stuff in your picture. We should probably include all of what we did, which are the X and Y intercepts, the vertices, and the foci. Let's do another example. This one's going to be slightly different. I want us to find an equation of the ellipse with foci plus or minus 3, 0, and vertices plus or minus 4, 0. So this problem is not asking us for a picture. It's not asking us for anything like that. We just need to write down the equation. So I want you to look at this, right? The foci and the vertices are both going in the x direction, right? So we know that it's going to be this type. It's going to be x squared over a squared plus y squared over b squared is equal to 1. Okay, what is a squared? We know that a squared is 16 because plus or minus a are the vertices, and we also know that c squared is 9. So what's b squared? Remember, that's always a squared minus c squared. So this is going to be, remember, a squared minus b squared is c squared, but that's the same as saying a squared minus c squared is b squared, right? So all I did is I rearranged this equation, okay? So b squared is equal to a squared minus c squared. That's 16 minus 9, which is 7. So this is my formula. We end up with x squared over 16 plus y squared over 7 is equal to 1. Okay, so pretty simple stuff, right? Let me give you an interesting aside here before we move on to our last conic section. So interesting aside. What if the foci become the same point. Now, that technically doesn't make sense, but what I'm trying to say is what happens if your two foci get closer and closer together? What does this shape morph into? So this means essentially that C is getting closer and closer to 0, right? But what does this mean? This means that your formula, your a squared and your b squared become the same, right? So this means that you end up with x squared over a squared plus y squared over a squared is equal to 1, which is the same if we multiply the whole thing by a squared, is x squared plus y squared is equal to a squared, and this just becomes a circle with radius a. So pretty cool, right? I mean, this makes sense. This is saying that when you have an ellipse, if you take one point and you let it approach the other, your shape is going to morph into a circle. And that distance, of course, being your A. Okay, pretty neat. Pretty neat here, I think. Okay, and this is sort of intuitive, sort of like an ellipse you can think of as a stretched out circle, even though the definition is entirely different, right? Okay, let's do our last conic section here. I want us to talk about hyperbolas. So again, we're going to fix 2 points, F1 and F2, on the plane. And we're going to call them foci again. Okay. We're also going to fix a positive constant K. So what is a hyperbola? A hyperbola is the set of all points P in the plane that satisfy the following property. The distance from P to F1 minus the distance from P to F2 is equal to K. You'll notice this is just like our old definition for an ellipse, except it's a minus instead of a plus. Now, in order, you might be noticing, wait a minute, this would create something asymmetrical, right? Because the subtraction is only going one way. How do we decide which is the first one? So we don't actually care what the order of the subtraction is here. In other words, if we subtract two things, we want going the other way to be okay too. In other words, we should be able to get a plus or a minus k, and that's okay. So the way we fix that is by doing this. We put an absolute value there, and now we're saying that the plus or the minus k is fine when you subtract these things. Okay, so this is the definition of a hyperbola. So let's go ahead and derive the equation. Okay, so let me do this on the next, or actually let me start it here. We're going to do the equation derivation. And this one I am going to skip a lot of steps, okay, because the algebra is really similar to the last problem. Okay, so equation derivation, we're going to say that the foci are going to have points plus or minus c, 0 again. And we're going to let k, the constant, be 2a again. Okay. And we're going to say, let's suppose that P, which has coordinates x, y, is a point on the hyperbola. So let's go ahead and set up our, we know that we want P to F1 minus P to F2 to equal 2A, right? So what would this become, right? This means that the square root of x plus c squared plus y squared, right? That's the distance, minus the square root of x minus c squared plus y squared has to equal plus or minus 2a. Okay, now before the plus or minus scares us, remember when we actually square both sides and do our algebra, the plus or minus will go away, right? Because any time that you square a plus or a minus, you end up with a positive here. So we are not going to show all the steps this time, okay? After the algebra, so let me just say after. The reason I don't want to show it is just still going to be a lot of repetition, okay? So after a similar algebraic approach, we get the following. X squared over a squared minus y squared over, this time we get c squared minus a squared is equal to 1. Okay, so again, what we're going to do is we're going to give this guy a name, okay? We're going to call this guy right here b squared. In other words, we're going to say let b squared equal to c squared minus a squared. So this leads us to the following. We end up with x squared over a squared minus y squared over b squared is equal to 1. And we also have the following relationship. Our relationship is different now with a and b. We end up with this. Okay? So this is our formula for a hyperbola. Okay? So I want you guys to notice something else about a hyperbola, right? Because so far we have not drawn a picture of a hyperbola at all yet. But I want us to notice something. So notice that if we were to solve for x squared over a squared, this is equal to 1 plus y squared over b squared, which is actually larger than 1, right? Which means that x squared must be larger than a squared, no matter what x is. But how do you solve this? If you take the square root of both sides, you get the absolute value of this is greater than or equal to a, which, as we know from algebra, leads us to x being bigger than a, or x being less than or equal to negative a. What this means is that x must be larger than a or smaller than negative a. Can't be anything in between. So this means that a hyperbola has two branches, a left branch and a right branch. So left branch. The left branch is when x is smaller than negative a, and the right branch is when x is larger than a. Sorry, a little messy here. X is smaller than negative a, and the right branch is x is bigger than a. Now, what are the x intercepts of a hyperbola? Well, when you plug in y equals 0, this means that x squared over a squared is equal to 1, which means that x is equal to plus or minus a. And so that leads us to our x intercepts. It does not have any y y-intercepts, right? Why does it not have any y-intercepts? Because remember, it has two branches. X is bigger than a or less than negative a. In other words, it can never be 0. So we've got our picture. Our picture actually looks something like something like that. And our foci actually lie inside this time. So it looks like that. So question, does the function have asymptotes? We're finally going to get to use a little bit of an idea from calculus, okay? So what I want us to do is let's look at y over x. So if we were to solve for y in the equation that we got above for the hyperbola, we end up with the following. We get y squared is equal to b squared over a squared times x squared minus b squared. So this is what we get, which means that y is equal to plus or minus b over a times the square root of x squared minus a squared b squared. So what is the limit as x goes to infinity of y over x? This is equal to the limit as x goes to infinity of, we're going to divide this guy by x, okay? So that's going to give us plus or minus. When you divide that by x, that's like taking out an x squared from the radical, and so you end up with 1 minus a squared b squared over x squared, right? And so if you send this guy to infinity, then that means this guy goes to 0. Oh, my b over a disappeared. Sorry, this is important. So plus or minus b over a. What do we end up with then? We end up with b over a. Plus or minus. This is really important. This means we have just found out that the slope, remember the slope is y divided by x, right? What we're saying is that as we go out to infinity, y over x approaches plus or minus b over a. So this means that y is equal to plus or minus b over a times x are the asymptotes. What are asymptotes? Remember, asymptotes are curves that are, they're lines or curves or something like that that our function approaches but never touches. The reason we got a plus or minus is because actually, depending on, so I kind of cheated a little here. When I divided by x squared in the radical, this is where we actually got, we actually made an assumption that x was positive, because when we divided by x and we were sending x to infinity, we were assuming x was positive, right? But if we go to negative infinity, that means everything becomes negative, and that's where we get the negative in the plus or minus from. Okay, so we've got our asymptotes, and now this leads us to, I want to give the hyperbola summary here, because now we know everything about them, is that if we have x squared over a squared minus y squared over b squared is equal to 1. And remember, we know that a squared plus b squared is equal to c squared. We have what we call the vertices, and the vertices of a hyperbola are plus or minus a 0. And we have the foci, which are going to be plus or minus C0. And we also have the asymptotes, which is going to be y is equal to plus or minus b over a times x. Okay, what does this look like? So here's the way it looks, right? How do you draw this? I usually teach students, remember, when you're doing an asymptote, rise over run, B would be the rise and A would be the run. The easiest way to do this is to just draw a box since we're going in both directions. Now remember, A and B could have any relationship. It's not like an ellipse where A is larger than B. Okay, so let me just go ahead and draw A as if it were bigger than B, but it doesn't have to be that way. So here's the way I always suggest to students. I say draw a box. The box must cross, if this is going to be, so this is going to be B, negative B, this is going to be A, negative A, right? And then we're going to connect the diagonals of the box with a straight line, and what we've just done is drawn the asymptotes, right? Because think about it, these lines have rise over run of B over A, B and A, right? So these are the asymptotes. They go through the corners of your box, and now we're ready to draw our hyperbola. Hyperbola are always going to start right at the box, and then they're going to approach these lines, but they're never going to touch it. Okay. Where are your foci? Your foci are, of course, somewhere in here. They're not technically considered part of the hyperbola, but they are an important feature. Okay. Okay. So this is all the important stuff about a hyperbola. Now, how can you tell that the hyperbola is oriented horizontally like this? It's got a left branch and a right branch. You could tell because the x squared is subtracting the y squared. So you could tell by the one that's positive and the one that's negative. Okay? So let me say it this way, right? So if we interchange, so interchanging x and y yields, we get y squared over a squared minus x squared over b squared is equal to 1. So this is what happens when you interchange x and y, right? So now what happens? Your foci are 0 plus or minus c. Your vertices are 0 plus or minus a. And your asymptotes. What happens is, if you replace your x with your y, you actually get y equals plus or minus. So think about it this way. You had y equals plus or minus b over ax, right? So if you interchange it, it becomes x equals plus or minus b over a y, but then if you solve for y, the a over b gets flipped to the other side and you get the reciprocal, so you end up with y equals plus or minus a over bx. Same thing, by the way, as if you were to just flip the x and the y. So you really are just interchanging x and y here. That's all you're doing. Okay, and again, when you do this, your foci, 0 plus or minus c, 0 plus or minus a. So let's say this is a, and let's say that b is right here. Again, it could be any size. Do your box. And it's going to look something like I used blue last time. Let me do it again. Why not? Consistency. So instead of a left branch and a right branch, we have sort of an you can call it an up branch and a down branch, or northern and southern, whatever you want to call it, right? We have two branches still, right? Up and down. And just to write down some coordinates here, I used red before. So this is now 0a, this is 0, negative a. This guy is b0, this is negative b0. And our foci is somewhere inside here. This is 0, c. This is 0, negative c. And again, don't forget our relationship does not change. A squared plus b squared is equal to c squared. Okay, let's do a quick example here. Let's call this, this is problem 4. I want us to find the foci and asymptotes of the hyperbola 4x squared minus 9y squared is equal to 36. So again, don't be too concerned here. What I do is I divide the whole thing by 36. We want to get a 1 over there. That's always the key for actually both ellipse and hyperbola, right? So if we divide everything by 36, we end up with x squared over 9 minus y squared over 4 is equal to 1. And because the x is positive, we know that this is going to have the left branch and the right branch. So then this would be your a squared. This would be your b squared. And we know that c squared is a squared plus b squared. So that's 13. So what would the foci be? Plus or minus square root of 13 comma 0, right? So this would be your foci. What about the asymptotes? Well, x comes first, right? So it's the horizontal branch. This was what we called sort of the normal case, right? So the asymptotes are y is equal to plus or minus b over ax, in other words, 2 over 3 x. So these would be your asymptotes. Pretty simple, right? It's not too bad once you get familiar with those equations, and I'm hoping that you guys remember this stuff from before. Okay, let's do another one. Find the foci and equation of the hyperbola with the vertices 0 plus or minus 1 and they give us one asymptote, y equals 2x. Okay, so the key here is trying to figure out from this information what form we take on. Because we notice that the y part of this is changing, right? Changing y part here, that since we have a fixed x is 0, we know that this is going to be the following type. We know it's going to be y squared over a squared plus x squared over b squared is equal to 1. So this is what we know. Okay. We know it's that type, and not only that, but we know what a is, right? A squared has to be 1 squared, which is just 1. And so we end up with y squared over 1 plus x squared over b squared is equal to 1. And what are the asymptotes for this type of equation? Remember, the y came first in this one, right? So this is the swapped kind. So this means that the asymptote equation, the asymptotes are going to be y equals a over bx, right? Y equals plus or minus a over bx. But they told us that one of them was y equals 2x, which means that a over b has to equal 2. But we already know that a is 1, so 1 over b is 2. So this means that b is a half. In other words, b squared is 1/4. Okay, so we're getting there. We're almost there, right? We know that a squared is 1 and b squared is 1/4. So finally we can do c squared. C squared is a squared plus b squared, which is 1 plus 1/4, which is 5/4. So we're ready to write down our answer then. Our equation of the hyperbola that it asked for is going to be y squared over 1 plus x squared over 1/4 is equal to 1. So there's our equation. And what's our foci? It's going to be 0 and plus or minus c. C is the square root of 5/4, right? So it's going to be plus or minus root 5 over 2. Here we go. Okay, these problems are kind of fun. It's almost like a puzzle. The last concept I need to talk about, I know this is a long video, but the last thing I want to talk about are translations. Every single thing that we wrote down can be translated, right? So let me just remind you guys that when you take x and you translate it to x minus h, this is called a horizontal translation of h units. So if h is positive, we move to the right, and if h is negative, we move to the left. Okay. If you replace y with a y minus k, then this is a vertical translation. K units. If k is greater than 0, it's up. If k is less than 0, it's down. So all of the problems that we did are completely symmetrical when it comes to reflections, but except for the parabola. Just remember that, oh no, actually, we don't even need to talk about reflections. I apologize. That's because when I taught you the parabola, I told you what happens when p is negative versus positive. So yeah, we don't have to talk about reflections. So the point is here that every equation we wrote down can be adjusted by a translation. As an example, for the ellipse, it can become something like this. So this is exactly what we did before, except everything is translated by h and k, right? So it's almost like h and k acts like the new origin in our problem. So I want us to do a couple of examples taking reflections into account, translations into account. All right, so This will be example 6. Find an equation of the ellipse with foci 5, 3 and 5, 5 and one vertex at 5, 9. Now, when it comes to a problem like this, I highly recommend just drawing a picture of what you know. Even though the problem doesn't ask us for a picture, it could really help to look at what the translation actually is, okay? So if we look at our picture here, 1, 2, 3, 4, 5, 1, 2, 3, so we've got a dot right there, 5, 5. It's right there. Already, if these are the two foci, we know where the translation has to be right here. In other words, our HK has to be 5, 4, doesn't it? Because we know that usually the origin sits right between the two foci, but here it has to be that. Okay, now what about 5, 9? I would go ahead and plot that on our graph because, so 1, 2, 3, 4, 5, 6, 7, 8, 9, there it is. Why would I want to graph that? Well, it's going to help us because we're going to be able to figure out what A and B are, because remember, A and B is with respect to the translation, right? So what does this tell us? So if this first guy was the focus, this means that C is 1, and what about that guy? That's A. That tells us that A is, how many spaces is that? Let's count. We're going from 4 to 9, and so that would be 5 spaces. So A is equal to 5. There's a lot we can tell from a picture, right? Or even from just these 3 dots. We also know that if that's a vertex, the other vertex has to be on the other side, 4 down from here. And so we know that this is going to look something like this. We don't know what B is, so again, I'm just guessing here. But the point is this. We know it must be a vertical stretched ellipse, right? Because the foci and the vertex were in the direction of Y, right? They were all going up and down. Okay, so let's write down what we know. We know it's y squared over a squared, so over 25, plus x squared over b squared is equal to 1. We don't know what b is yet. So how do we find b? Well, b squared is always equal to a squared minus c squared in an ellipse. So this is equal to 25 minus 1, which is 24. So there you go. We've got our equation. Our equation is y squared over 25 plus x squared over 24 is equal to 1. Okay. Really not that bad. I highly recommend drawing a picture for these kinds of problems where there's a translation, because that's going to be a lot easier than trying to memorize 1,000 formulas and trying to just figure out algebraically what it is. You could miss something really obvious here. Okay? All right. By the way, as an aside, since 25 and 24 are so close to each other, this actually is only a barely stretched out circle, right? So anyway, that's worth noting. My picture is definitely not accurate here. Okay, let me do one more example. This will be a good problem to see. I want us to sketch the conic 9x squared minus 4y squared minus 72x plus 8y plus 176 is equal to 0. Note, it's not even easy to tell what type of conic this is, right? And so this is going to involve a technique, you guys may remember it from earlier math classes, called completing the square. We've done it very little in this class, probably when we learned how to do trig substitutions. We did a little bit of that in our hardest examples, but here's how this is going to work, okay? What we're going to do first is we're going to group the x terms together like this. Right? I'm taking these guys and I'm writing them next to each other. And then I'm going to take the y terms and write those next to each other. So this, and I'm going to give it some space here. Oh, sorry, this should be a minus. Okay. And then I have a negative 176 on this side. So here's what we do. What we do is we actually factor out. Now, before I write the rest down, I'm going to go ahead and complete the square. The way we do this is take that middle term. I have an 8, and I divide it by 2, and then I square it. So this becomes 4 squared, which is 16. So I know I'm going to add 16 to this. But then I also know that I have to subtract 16, right? You have to do the same thing to both sides, okay? Now on this guy, I'm going to factor out a negative 4, and I'm left with y squared minus 2y. And here is my new middle term, so I'm going to do negative 2 divided by 2 and square it. And that gives me, you know, it doesn't matter. The negative doesn't matter because we're going to square it anyway. It's always a positive what you add to it. So this is going to be plus 1 minus 1. So this is what we have. Now what? I factor this guy. This becomes, well actually, let me not factor it first. What I'm going to do is I'm going to break this guy out. What's 9 times negative 16? So 9 times negative 16. It's negative 144, right? So negative 144. Minus 4 times y squared minus 2y plus 1. And then I'm going to break this guy out. Negative 4 times negative 1 is positive 4. So this is what we have. Now I'm going to take this guy and move them over and combine it with the negative 176. And I'm going to take these guys and factor them. So this becomes 9 times x minus 4 squared minus 4 times y minus 1 squared. And what do I have on the right? I have negative 176 plus 144 minus 4, which is, get my trusty calculator here, I get negative 36. Finally, I divide everything by negative 36 because I'm trying to get a 1 over there. And this is what I get. I get a 1. And because of the negative, I'm actually going to write, so it goes like this, right? X minus 4 squared over negative 4 plus y minus 1 squared over 9 is equal to 1, right? And we finally put it in our right form, and we notice this has to be a hyperbola because we've got a negative and a positive, but it's in the wrong order, right? You always have to put your positive 1 first. So it's going to become y minus 1 squared over 9 minus, and then the other one's going to be x minus 4 squared over 4 is equal to 1. So we know what our translation is. Our translation is 4, 1. 4, 1. Everything's going to be with respect to 4, 1. Okay, so the easiest way I can think to do this is let's go ahead and draw 4, 1 here. So 1, 2, 3, 4, and 1. So we're right here. Okay, and now this is going to be our a squared, right? This is a squared. A squared is 9, so which means I'm going to move 3 up and 3 down, right? Because a is going to be 3. So 1, 2, 3, 3 up, 1, 2, 3, 3 down. And then this guy is b squared, and this means I'm going to move 2 to the left and 2 to the right. Now remember, this is going to be just used to draw our asymptotes. It's hyperbola, right? So it's a hyperbola. Let me also say that we have, a left and right. Oh, sorry, no, up and down, up-down branches, right? We've got our, sorry, that line doesn't look straight. I should have done a better job. Something like that. And if we draw our actual hyperbola, it looks like there we go. And let me go ahead and label some stuff here. What point would this be? This is 4, 1, 2, 3, 4, right? 4, 4. And then this other one is 4, -2. Points are going to have weird coordinates when you have translations. This is why it's important to draw a picture for one. This point right here is 1, 2, 3, 4, 5, 6, 1. And then this point is 2, 1. What about the foci? We haven't even talked about that yet. It's not that bad. C squared is a squared plus b squared, right? So that's going to be 9 plus 4, which is 13. So C is plus or minus root 13. The foci are 0 plus or minus root 13. What is the square root of 13? It's 3 point something, right? Square root of 13 is, let's see here, what is it? 3.6, right? Approximately. Is that correct? 3.6? Yeah, 3.6, that's right. So, sorry, I messed up here. It's not what, it's plus or minus root 13 from the foci, or sorry, from the translation. I apologize. So the foci, I'll show you what the coordinates are in a second, but what we're going to do is we're going to move square root of 13 from the 4, 1. So that puts us at 3.6 above the 4, 1. So it's something like right over, so it's like right here, right? So 0.6 above that, and then 0.6 below this. So what would these points be? Just put a 4 and then a 1 plus or minus root 13, right? Because it's getting added to the y. So this would be 4, 1 plus root 13. And this other point would be 4, 1 minus root 13. So these are the foci. Again, guys, it's hard to tell what your conic is just from looking at your equation. This is why we needed to complete the square. For those of you really paying attention, if you notice, these two did have opposite signs right from the beginning, so we knew that it was going to be a hyperbola. However, we didn't know whether it was going to be an up-down hyperbola or a left-right until you finish putting it in standard form. This standard form gives it all away, right? As soon as you can put it in that form, practice your completing the square, and as soon as you can put it in that form, you should be able to tell everything there is about the hyperbola, or any of the conic sections, really. Okay, guys, thank you so much for watching this long video. I hope that it was informative. Thank you.